Yeah, so now the next chapter is intermolecular forces and allotropy. This is again a very interesting topic in which we are going to study about the various forces which exist in between the molecule and between the molecules, different molecules, and the phenomenon of presence of different physical forms of a particular element. That's called allotropy. So we are going to peep into that. So first of all, now, what is it that sometimes now we know that, just a second. I think I have, yeah. So, see, now we are very much sure about, or we are very much clear about the thing that the compounds are ideally of either ionic in nature or they are covalent in nature, right? So we know that the covalent compound, right? The properties were very much, they were influenced by the intermolecular forces, which we used to say ki there was the force which was present between the different pair of molecules, right? For example, I know melting point, boiling point, right? They are all dependent on the kind of the strength of the intermolecular forces being present, right? So that is very, very independent because obviously, if a substance has to be boiled, the intermolecules need to be freed from each other. So we need to supply that much of energy, and obviously that determines the strength of the boiling point or the melting point, right? Now, elements, like if I talk about the carbon, now carbon is this, and physically it is present in three forms. It can be more than three, but yes, ideally we talk about the three forms. One is diamond, right? Other one is graphite, and the third one is fluorines. So this is a phenomenon in which carbon is present in different structures, leading to different physical properties. And these forms, different forms of carbon, they are called as allotropes, and the phenomenon is called as allotropism, right? Although they are made up of the same elements, carbon, but the arrangement of carbon, arrangement of carbon is different, thereby leading to different physical properties. So that is very interesting to know. Now, for example, if I say diamond, diamond is the hardest known substance, right? It is very hard. And its structure is like this, now, it does not have any free electrons. So that is the reason why it's a bad conductor of electricity. It will not conduct electricity because there is no presence of free electron, right? But in case of graphite, because of its structure, it acts as a lubricant. It acts as a lubricant as well as a good conductor of electricity. It is the only non-metal form which is a good conductor of electricity. Otherwise, non-metals, they are known to be bad conductors of electricity, right? So graphite being a good conductor, it is used as an electrode also, right? And fluorines, they are very big molecules. For example, uh, I have one molecule which is composed of 60 atoms of carbon and they are arranged in a spherical shape, just like a football, right? And that name is Buckminster fluorine, right? Buckminster fluorine. This is also another allotrope of carbon having different physical properties because of the different structure present, right? Now, if I'm talking about the covalent bonds, right? Now, covalent bonds are basically formed when there was sharing of electrons, right? When the things were like we could not lose or gain electrons because of the energy involvement. So the element preferred to share the electron, right? For example, if I talk about methane, right? Initially, we are going to take about methane. Uh, if you remember, the formula was CH4, right? This was methane. Okay. Now what happens? Carbon has got four valence electrons in its valence shell, right? Whereas hydrogen has got only one electron in its valence shell. So this hydrogen needs one more electron to complete its duplet, right? According to the duplet rule, hydrogen and helium, they are going to complete their valence shell only by two electrons, right? And rest of the elements, they go with the octet rule. According to that, the valence shell should have 8 electrons. Now see what happens. This hydrogen is going to take help from carbon and will share its own electron and also take the help from the carbon's one electron. Similarly, this hydrogen is also going to do the same. The same procedure will be followed by this and this one. So now all the hydrogens, they are complete, like they have completed their valence shell, right? They have got two electrons in their valence shell. Now what happens to the carbon? Now carbon will say, I am going to reciprocate the same thing. So now carbon has got 8 electrons in its valence shell, 4 of its own and 4 of the hydrogen which is being shared, right? So there is one pair of electron being shared. This is also one pair. This is one pair. This is one pair. At one moment, there is only sharing of one pair of electron. So this is your single covalent compound, right? Single covalent compound, right? So this is a very good example of covalent compound. But now hydrogen and carbon, their electronegativity difference is not much. So I cannot say that hydrogen is more electronegative as compared to carbon or carbon is more compared to hydrogen. No. So here the sharing will be such that the shared pair of electrons will lie in between the two elements. So there is no shifting of the shared pair of cloud, thereby leading to non-polar covalent compound, right? Non-polar covalent compound, right? Now, on the same similar lines, I'm going to talk about HCl now, right? HCl is hydrochloric acid, right? Okay, HCl, HCl. Now, I know H has got only one electron in its valence shell and chlorine has got 7 electrons in its valence shell. Now, according to octet rule, chlorine requires one more electron, whereas hydrogen also requires one more. So they just come to this thing that we are going to share the things, so that would make our work much easier. So now hydrogen has shared one electron which it had. So hydrogen's duplet is complete. Same thing will happen with your carbon, chlorine. So chlorine is now going to share the same pair of electron, thereby completing its octet shell, right? Now, both the things are okay. There is one pair of electrons being shared. We know that it is single covalent compound. But in this case, in this particular case, this chlorine, na, it is more electronegative in nature, right? Now, what do you mean by electronegative? Electronegative was the ability of a particular element, to attract that shared pair of electrons towards itself. Okay, right? So now chlorine is more electronegative as compared to hydrogen. So what it will do, it is going to, share, just attract that shared pair of electrons towards itself. Thereby, there will be a very slight charge popping up on these two elements, because now shared pair of electrons is more towards chlorine. So that means there is an extra electron on the side of chlorine. So chlorine is going to have a slight negative charge, whereas hydrogen will have a slight positive charge, right? So thereby this covalent compound becomes polar in nature, and we say this compound is polar covalent compound, right? Another example for this is your water. Then you have hydrofluoride, then hydrobromide, hydroiodide. All the halogens, they are very, very electronegative in nature. They have this tendency to attract the shared pair of electrons towards itself. So they just, love to have some charge on them, right? So halogens, they are very, very, good electronegative elements. So now these now the polar molecules, they have some charges on them, and naturally, in addition to the intermolecular forces of attraction, there will be the forces of attraction resulting due to development of charges. That also leads to very strong bond, right? Sometimes what happens, uh, we have covalent bonds between the same atoms of the same element. Like, for example, if I talk about nitrogen, right? Nitrogen, it forms, like, it shares 3 pair of electrons to complete its respective octet shell. So this is a covalent molecule, right? It is not a compound, it is a molecule, and it is going to be covalent in nature, right? Now, what happens is, see, uh, I know polyatomic molecules. That means which is like there is presence of more than two atoms. So the presence of the polar covalent bond doesn't mean that the molecule is going to be polar in nature, right? Sometimes what happens in the molecule, na, there may be presence of one or more than one dipole, and that would cancel out each other. Okay? So shape of the molecule, right? That is determined by the net dipole moment, right? So just note this point. Shape of molecule, the covalent molecule, is determined by how it is the net dipole moment, whether the dipoles they are canceling out each other or they are simply adding up. So that determines your shape. Is that clear?
Yes.
Okay. So let me wipe this off so that we can move ahead. Okay. I hope you had written.
Yes.
Okay, then it's fine. Now see, when we talk about water, water molecule has also, two OH bonds, right? Water molecule is written like this, and what happens is O and H. There will be two dipole moments are there between one oxygen and hydrogen on one side and one oxygen, the same oxygen, and another hydrogen on the other side. So this oxygen will have a slight negative charge because of its more electronegative nature. Similarly, hydrogen will have a slight positive charge, both the hydrogens, right? Now what happens is these molecules, they are going to have a net dipole moment. Thereby, the shape will be like this. This is the shape of water molecule. Okay. Similarly, if I talk about ammonia, ammonia is ammonia is written as NH3, and N will form covalent bonds with three hydrogens, right? One hydrogen like this, then this, and this one. So this hydrogen, and this hydrogen. Now nitrogen will have a slight negative charge on it. Hydrogen will have slight positive. All the hydrogens will have slight positive charge. So net dipole moment is going to give us the shape like this. So there is a shape in which the three, like this is nitrogen, and the three hydrogen atoms, they are inclined like a tripod, right? They're attached like this. If I talk about BF3, which is boron fluoride, in that case, boron is having slight positive charge, and fluorine, because of being a halogen atom, it is going to be more electronegative in nature, and hence a slight negative charge on it. So they have like this, right? I'll make this charge over here, right? Now, what happens is, in this case, there is no net dipole moment. The dipole net will be equal to 0, thereby they are going to cancel out the thing, and hence these bonds, they would be at the same angles and at the same distance between each other, because there is no net dipole moment. Here you have the different distance between the two type of bonds, right? But in case of BF3, right, you don't have net dipole moment. Net dipole moment is 0. Therefore, all the bond angles will be equal, right? Similarly, when we talked about the methane also, what happens is, because hydrogen is not that much electronegative in nature, right? Similarly, carbon is also not. So there is very, very less chances of having the dipole moment. So what we say, because of slight difference, there will be charge, but the charge will be too less to be, taken into account. If we say that this is delta negative, this is delta positive, this is also delta positive, because hydrogens, they are going to have slight positive charge. So in this case, the net dipole moment already weak in nature, but it is going to cancel out also. So net dipole, there will be zero net dipole moment. Okay? There will be no dipole moment acting on. So there is the distance between the bond angles are equal and the hydrogens will be at the equal distances from each other, right? So tetrahedral shape, right? So in the case of tetrahedral shape, na, most of the times the net dipole moment will be cancelling out each other. Methane, we know it's a non-polar molecule because it does not have any charge on it. So, in order to satisfy the structure being shown by the molecule, we just say carbon, we suppose that carbon is going to have a slight negative charge and the hydrogen will have slight positive charge. Otherwise, it's a non-polar molecule, as we studied just before starting this topic, right? We know methane is not a polar covalent compound. It is a non-polar covalent compound, right? Got it now? So what happens? Now we can have one more definition of polar and non-polar. See, in polar molecule, for example, ammonia, water, boron, fluoride, trifluoride, right? There is a net dipole moment. Or I can say, if a molecule has net dipole moment, then the molecule is said to be polar in nature. Got it? So every time I need not learn, otherwise it is very known thing that if the electronegativity difference is high, then the compound is going to be polar covalent compound, right? Molecule. So I have this thing, if a molecule has net dipole moment, or I can say it has dipole moment greater than zero, so it is a polar covalent molecule. Got it? Similarly, if there is no net dipole moment, or I can say there is the net dipole moment is zero, that means the molecule is non-polar in nature, right? So we can just sum it up like, okay. So polar means there should be presence of net dipole moment, okay? And if I'm talking about the non-polar, so this means there will be absence of net dipole moment, or I can say the net dipole moment will be zero, right? Now, if I want to see, I want to check whether a given, particular molecule is polar or not. What I need to keep in mind, number one, is there any presence of polar bonds? Okay. Number two, if there is presence of polar bonds, then I have to see whether they are cancelling out each other or they are simply adding up or subtracting, giving it a net dipole moment. Which means, first of all, I'm going to clarify whether there is presence of polar bonds or not. If I come to this conclusion that polar bonds are there, right, but they cancel out each other, so it will be non-polar. But if doesn't cancel out, right, then I would say ki yes, the compound, the molecule is polar in nature, right? So when I have to see ki whether the polar bonds are present or not, now what I have to see, I'll have to ask the elements, are you involved in polar molecules or polar bonding? Elements, they cannot answer me back, right? Carbon or chlorine, they're not going to tell me, hey, buddy, I am forming the polar bond. No, I need to learn this. How? I told you the electronegativity, right? The phenomenon of electronegativity. So when I have to check whether the polar bonds are present or not, what I need to check? I need to check the electronegativity difference. Higher the difference between the two entities, the more chances of having a polar bond will be there. Got it? Right? And the second, when I want to, confirm whether the net dipole moment is zero or it is not zero, okay, then what I have to see? I have to see the shape of the molecule, right? Like, for example, in tetrahedral shape, when I know the bond angles are equal, right, that means they are aligned at the same distance, which means there is probability of the cancelling out of the dipole moment. So that I need to keep in mind. So what I'm going to keep in mind, the two things. One is the electronegativity. Number two is the shape of the molecule, right? Which is going to tell me whether a given molecule is polar in nature or not. Is that clear?
Yes.
Yeah. So first of all, we are going to wipe off this. Okay. Now we are going to study about this, how to, the relationship between the electronegativity and the bond polarity. Although we are very much aware of that now, but still, theoretically, what is happening that we are going to see now, right? Okay. See, now, what happens? A covalent bond, we know that it is formed because of the sharing, right? There is sharing of electrons when the element is energetically not in a position to lose or gain electrons. So it tends to mend its way and naturally it has to attain stability, right? Stability, though it wants to have, but how? Now it is going to share the electrons. This is the way it has chosen up. Now, if the two partners, if the two sharing elements, right, the elements who are contributing to the sharing of electrons, out of that, the one who is more electronegative, that means that it is going to attract that shared pair of electrons towards itself, right? So that means if the electron is being attracted by a particular element, right, then we say it is a measure of electronegativity. Okay, it is the measure of electronegativity, right? Now, electronegativity, now, like we know, there is, the shared pair of electron is being tilted towards that more electronegative element, right? Now, values are there. We have to learn somewhere. We have to be, keep in mind. For example, if I say fluorine is the most electronegative element, right? Because of its very small size, now it is very, very, very keen on attracting that shared pair of electrons towards itself. Now, they have given us this descending order of electronegativity: fluorine, then oxygen, then nitrogen, which is equivalent to chlorine, then bromine, carbon, which is just approximately equal to sulfur, iodine, then phosphorus, hydrogen, and last is silicon, right? So naturally, the more common, see, there are some elements who are more commonly, involved in the polar bond formation. They are hydrogen and oxygen. They're very good, you know, carbon and, sorry, hydrogen and nitrogen in case of ammonia, right? Then carbon and oxygen. They're also very good examples for forming a bond, polar bond, right? Carbon and chlorine in the form of carbon tetrachloride, right? It's a very good compound. Now, the the one having the slight positive charge on it will be named first, right? It's a rule when you name a compound, na, the cation has to be, placed at the first position and then anion, right? Okay, so now we know that the polar thing is, you have to keep in mind the electronegativity in nature. So that descending order, na, just learn it. When you are going to read it for 2 or 3 times, na, you're gonna have some idea about that. Ki yes, this one is having more electronegative values as compared to the other, right? Now, if I want to predict the shape of the molecules, how it is going to help me, right? First of all, see, there are so many techniques which are there to determine the shape of molecules. Now, chemistry is actually fun when you are talking about the molecules, you're talking about the formation of a compound, and at the same time, you're saying that the compound which is formed, you can just imagine its shape. That's fascinating, na? If I talk about water, now water, though, what would we do? We put it in glass and have it. Now just think about that. You know about how it is being formed and what's the structure of that molecule. That is so fascinating, right? Now, when we are like, see, we had very many techniques to identify the shape of the molecules. So we just predicted the shape and analyzed so many shapes, and finally we got to have some, principles based on those experiments, right? Some principles, some rules, you can say that, so that it becomes more easier to, explain the phenomenons which were shown by those compounds. Now, for example, the very first thing, the very first point which is being given: pair of valence electrons around an atom. See, any atom of an element will have valence electrons, right? Now, we are going to pair up the valence electrons. Okay, first thing clear, we are going to pair up the valence electrons. Now, they arrange themselves so that they are going to be as far as possible, right? See, electrons, they have negative charge on them. Just understand this thing. Electrons, now see, for example, in valence shell, I have 7 electrons, right? We assume this, or we can just say that 4 electrons are there. Okay. Now, all the 4 electrons, they have negative charge. They have negative charge, right? And I know the like charges, they are going to repel, right? They don't like their company, right? Similarly, right? So what they do, they would try to sit as far as possible in the shell. They're not going to sit all together, the 4 electrons, right? So what they are going to do, they're going to align themselves. The distance is like the max distance which I can afford. And this is the most determining factor in the shape of the molecule, right? And this is called valence shell electron pair repulsion theory. Okay, what it says actually. See, hmm? Okay, Hanji, Vesper theory. We call it by love. It's Vesper theory, right? Who will say this such a long name, right? We call it very by the nickname called Vesper theory. Now, Vesper theory, I'm again telling you one thing. Valence electrons, right? What we are saying, valence electrons, first of all, they are the electrons present in the last shell. Okay. The last shell is your valence shell. Okay. Now, electrons, they have negative charge on them,
Okay.
right? And second thing which I have to keep in mind, like charges repel each other, right? Now, these valence electrons, what we are going to do, we are going to pair up, right? Now, the paired valence electrons, right? Now, they are going to arrange themselves in a way that they are as far as possible from each other, right? But what's the point of this? Why they are doing this thing? Now, I always tell one thing. You study a branch of science, be it physics, be it chemistry, be it biology. Everything is going because of the energy involved. Got it? See what happens. For example, I'll take you an example. I'll give you an example which is more related to the daily living, right? Suppose we have like we are 4, 5 siblings, right? And you know, siblings they fight with each other a lot, right? Over petty issues, right? Now, what happens? Our parents will say, "Ki, you just sit as far as from each other as possible," thereby reducing the fights to the minimum. It happens, right? Suppose we are in a class and we don't, gel with some students. So what we will do? We will sit at the maximum distance from them. So same thing happens with electrons. They are having the same charges. Hence, they are going to, repel. Unnecessary repulsion. If they are close enough, so what will they do? They'll just keep on repulsing from each other, right? Thereby leading to wastage of energy. Unnecessary, right? So when I have placed at a particular distance where their interaction is minimum, so that is going to give them stability, right? There will be, that position will be the most stable, or I can say it is of the lowest energy being involved in that, right? So this arrangement is why it is, when science, see, whenever some theory is given, naturally the scientists are going to question you. Okay, why you are saying like this? Why the electrons are going to arrange themselves like this? So the key point was given, the key point which was given at that moment was that there is involvement of stability, right? And that stability, how it, came into being. It was the lowest energy state, right? So this lowest energy state was preferred by most of the elements. Like, for example, I talk about beryllium chloride, right? Now, what happens? In beryllium chloride, I know, like beryllium atom, it has got two pair of electrons. So the most suitable arrangement, what will be the arrangement for electron? It will be like this. This is one shared pair of electrons, and here. This is the maximum distance, now, as far as possible, right? So what happens? It will form a compound with chlorine. Got it? So it will be this table. But now if it wants to, if I'm talking about the boron trichloride, what happens with that? Boron trichloride means boron will have three pair of valence electrons. Okay, so the ideal arrangement will be like this. This is the maximum distance which an electron can afford to have the lowest energy state, right? So if I have three pairs, got it? If I have the three pairs of electrons being, involved, then the most stable arrangement is planar. Okay? And planar, and that will be, just imagine ki, we can say, suppose we have an equilateral triangle. Equilateral triangle means the all three sides are equal, right? So I can say this is one chlorine, this is one chlorine, this is one chlorine. So they are going to be the corners of the equilateral triangle. So they have this angle of around 120 degree with them, right? Got it? Planar. I'm not talking about exact equilateral triangle, but I'm just letting you know that the distance between these will be equal. Got it? Na? In equilateral triangle, this angle is 60, but I'm talking about the boron and chloride angle. Got it? So that's why it is of 120. So boron trichloride, the shape of the molecule is planar and the bond angle is 120. Got it? Or simply we can say it is trigonal planar molecule. Got it? Right? Now,
Yes.
when we talk about the methane, now methane, though we have already done the structure, right? It is just like this is carbon, one hydrogen is there, then again one hydrogen, hydrogen, and hydrogen. So this is a kind of tetrahedral structure, right? Like this. Okay. So what happens is in this, when there is, involvement of four pair of electrons being shared, so the corners of a tetrahedron will be the most stable shape which that molecule can present to. Okay, so this is tetrahedron or tetrahedral, right? In this, the hydrogen, carbon, hydrogen bond angle will be around, oh, एक second. I had written and once again I'm writing. The bond angle is around 109.5 degrees, right? So this is the tetrahedral shape, which is having the least energy involved and hence the most stable shape for methane molecule. Okay, got it?
Yes.
Now, when we talk about ammonia, ammonia is particularly a very important molecule, right? In the way it has many peculiar things attached with it. First of all, see, ammonia, now in the formation of ammonia, nitrogen is having four pair of electrons around it, right? But the formula for ammonia is NH3. That means there is pairing of, sharing of three pair of electrons, right? So there are three bonding electrons and one lone pair is there. Lone pair is like, it is that pair of electrons which is not used in the bond formation, right? It is left being unused. Okay, I'm writing this thing. Lone pair of electrons and they really, affect the properties of that particular molecule. Lone pair effect. बहुत important है ये lone pair. You should be aware of that. So lone pair are the pair of electrons which are left unshared. Prisha, this is which? Okay.
Okay.
Yeah,
Yes.
with a bar in the down, right? Now, exactly what happens is, uh, I'm saying in ammonia, there are four pair of electrons involved, right? Four pair of electrons. And these four pairs are divided into two categories. One is your bond pair, and the other is lone pair. So bond pair are three, and lone pair is one. Okay. So
Yes.
if I'm saying four pair of electrons, abhi we just did the structure of methane molecule. In that also we had four pair of electrons, and we just got to know the shape of that molecule was tetrahedron, right? So we can say in case of ammonia also the shape can be tetrahedron, but no, it does not happen like that. Why? Because hmm? शेप टेट्राडी होते हैं, ज्योमेट्री अलग होती है. Okay. ठीक है. So now the shape of the four atoms is actually pyramidal in shape, right? Because of the involvement of lone pair of electrons. Okay. So in case of ammonia, it is pyramidal, right? So
Yes.
because of the lone pair of electrons, now I can see boron trichloride and ammonia. They both have three covalent bonds, three pair of, right? But shape is different. Why? Because of the presence of lone pair of electrons in ammonia, right? So that is giving the shape of pyramid. Got it? So that means when you are talking about the shape, you need to know about the total number of pairs of valence electrons. Got it? Okay. So water we are going to take up in the next class, right?